Hello guys, in this handout we want to draw different Newman projections and chair flipping of cyclohexane compounds. And the first question asks to build different perspectives and divisions of this molecule that you can see right here. So the first projection is sawhorse projection from rear side. That's going to be equivalent to the shape at the right bottom side of this manual that you can see right here. So if this is the side view of the same compound, you can see that the front methyl group is oriented a little bit or somehow toward upside, and the carbon that you can see right here turned down to the right, and you can see that both carbons here actually rotated counterclockwise, probably around 45 degrees, and finally gave us this new perspective of the same compound. So if you want to do that for the asked compound here, we need to draw a new shape regarding the new perspective. That's going to be like this one. We have SH at the top side, and then we have our first carbon. That's going to be this one, and this is the second carbon next to that. So we have the left bound with chlorine, the right bound with a methyl group. Then we have the connection with the second carbon like this. At the top side, it connects to this group that is one carbon and three methyl groups connected to that one carbon, like this one. Then at the right bottom of the second carbon, we have F3C. That's this branch from the side view, you can see right here. And at the left bottom, we have the OH or alcohol group, like this. So this is the sawhorse projection from the rear side. The second projection that was asked for was the Newman projection from the rear side. So we need to consider this compound from the rear side and look at the front and the rear carbon to create the Newman projection of that. So the front carbon for the Newman projection from the rear side will be carbon number 2, and the back carbon will be carbon number 1. So in the Newman projection, we have our circle. This is carbon number 2. OH. The left side, the left bottom side, and the right bottom side will be F3C. And our carbon number 1, that's the back carbon, connected to the second one. We'll have SH at the upside. Chlorine at the left side, and the methyl group at the right bottom side. And actually, I forgot to say, for the top side of the front carbon, or carbon number 2, there is 1 carbon connected to the 3 methyl groups. So it will be CCH3, 3. This is the Newman projection from the rear side. So the front carbon in this projection will be carbon number 2, based on the first side view compound that we have in the question. And the last projection will be the top view from rear. So the top view from rear, regarding whatever it is in the manual, will be this one. So we have one dash at the top side for our carbon number 2, one dash at the bottom side for our carbon number 1, the top bond will be the carbon with 3 different methyl groups, and the bottom will be for SH. Then for the carbon number 2, we have 2 wedges. So in the right one will be our OH bond, or alcohol group. The left one will be our F3C, and accordingly we have 2 left and right wedges for carbon number 1. That will be chlorine for the right wedge and methyl group for the left. And when you compare this projection or this viewpoint with the middle one, you can correspond all the relative connections and arrangements to their correspondent atoms, and double check that it's going to be correct based on the asked perspectives and viewpoints. Okay, the next part is on the page number 2, that asks us to first draw this molecule 777 3-fluoro 2-methylheptane 2-ol. We need to draw the zigzag or skeletal structure at first and number different carbons from C1 to C7. So we have 1, 2, 3, 4, 5, 6, 7 carbons. Then we have 3 floor or fluorine group. For carbon number 7, and 2-methyl for carbon number 2, 1-methyl for carbon number 2, and our OH group will be placed directly on carbon number 2 because the name of it is heptane 2-ol. So this will be the zigzag structure of the compound. There will be 4 different perspectives of the Newman projection of this compound based on our viewpoint from different pairs of the 2 carbons among all of the 7 possible carbons in the compound. For example, at B, we need to draw the Newman projection as if we are looking at carbon 2 as the front and carbon 3 as the back carbon. So in this perspective, at first we need to draw the main circle. So carbon number 2, if we look at the zigzag structure from carbon number 2, we see that there are 2 branches at the upper side and 1 at the downside. And carbon number 3, that will be the back carbon for this Newman projection, will be at the downside respect to carbon number 2. So we have this arrangement for our bond connections for carbon number 2 as the front and carbon number 3 as the back carbon. So here we have 1-methyl group. At the left, upper left are carbon number 2, and at the right side we have 1 alcohol group, and the downside we have 1-methyl group. So this is carbon number 1. Then we need to draw the rest of the structure from carbon number 3 up to the end that will be carbon number 7. So to continue the projection, we'll have carbon number 4, 5, 6, 7, and 3 fluorine groups. This is carbon number 7, number 6, number 5, number 4. So the other Newman projection is based on looking at carbon number 3 as the front carbon and carbon 4 as the back carbon. So in this Newman projection, we have the main circle, carbon number 3 is at the downside of carbon number 4, and there are 1 bond at the upper side of it and 2 different bonds at the bottom left and bottom right of that. 4 hydrogens like this. So we have this structure for carbon number 3. And the upper side will be all the other connections and bonds before 3 or before carbon 3. It will be something like this. So the alkyl group connected to the carbon here will be our carbon number 2, or will be related to our carbon number 2, like this one. And the 2 methyl groups, one is the upper side and the other one is the carbon number 1 as the other 2 carbons connected to number 3 at the upper side. And just pay attention, carbons number 2 and 1 are placed at the upper side or upper bond respect to carbon number 3. That's why they are placed right at the top side of that in the Newman projection. So the carbon at the back side of 3 is carbon 4 with 2 upper left and right connections, 2 hydrogens, and 1 down connection going up to the end of the compound, number 5, 6, 7. And there are 3 fluorine groups connected to the carbon number 7, as you saw before. The third Newman projection that we need to draw is looking at the structure from carbon number 7 as the front and carbon number 6 as the back carbon. So again, we need to draw the circle. And for carbon number 7, we have 1 upper bond and 2 left and right lower bonds. So the upper bond of carbon number 7 is carbon number 6, but at the same time it will be the back carbon for this. So we actually look at the structure from this angle. For this case, at first we have 3 different fluorines at the top and the 2 bottom sides of carbon number 7. So we have 1 fluorine at the top, the other at the left bottom and the right bottom. And then we have carbon number 6 at the back one, and it has 2 upper left and right bonds with hydrogen, as you see right here, and 1 bottom side goes to all the carbon chains before number 6, like number 5, number 4, 3, 2, and 1. And for number 2, as you know, there's 1 alcohol group or OH and 1 methyl group, like this. Okay, and the last one is the projection from carbon 5 to carbon 6. It's going to be like this one, the viewpoint from 5 to 6. So at first we have the front carbon as our carbon number 5 with 1 upper connection and 2 left and right lower connections. Regarding the position of carbon number 5, carbon number 6 is at the back side of that. So the upper side of carbon number 5 is exactly the bond and the connections for all the carbon chains before number 5. So we have this connection goes to number 4, number 3, number 2, number 1. The two upper connections for carbon number 6 will be the CH bonds, and the one lower connection will be the bond between carbon 6 and carbon 7. So we can see here, this is carbon 6 with two upper connections with hydrogen, and the connection on the lower side goes directly to carbon 7, as you can see here. And for carbon 5, we have one upper connection right here that goes to the preceding carbon chain before number 5, and the other two lower connections for number 5 are for hydrogens. And I forgot to mention that the two lower bonds for carbon number 3 at this projection will be two hydrogen atoms, and either for this Newman projection will be two hydrogen atoms. So in all the Newman projections, we have all the connections for every carbon atom that you can see right here. Question number 3 asks for drawing two chair conformations for each of these compounds you can see at the left side right here. So we need to change the carbons regarding the equatorial and axial bonds with other atoms and carbons. If we keep the same naming order that was given for this amine, we can say that this is carbon number 1, 2, 3, 4, 5, and 6. So we need to draw all the equatorial and axial bonds for each of those carbons right here. Equatorial, axial, axial, equatorial, equatorial, axial, axial, equatorial. For the first one, equatorial and axial. So for the first one, NH2 is connected as a wedge with respect to the surface of the ring, and That's the reason we need to put it as an equatorial connection bond here, because it's going to be placed at the top side of carbon number 1, and the only possibility to be at the top side of carbon number 1 in the chair conformation is placing as an equatorial bond like this one. The other ones are definitely the H bonds for the rest of the carbons. And for the second chair conformation, we know that every equatorial and axial bond will be exchanged to the conjugate ones. So every axial bond will be changed to the equatorial, and every equatorial bond will be changed to an axial bond in the other chair conformation. And regarding this logic, we have different equatorial and axial connection bonds here. So for the carbon number 1, if we start carbon number 1 from this side, for example, and number 2, number 3, number 4, number 5, and number 6, we have the amine group right at the top or at the upper side of carbon number 1. That's going to be only in an axial position like this. And the rest, equatorial and axial connections, are only for hydrogen bonds. So there's a big difference between the second and the first chair conformation in terms of the position of amine group. In the first one, the amine group is placed as an equatorial bond, but for the second one, it's placed as an axial bond. So we know that the bulky or every branch or every connection bond will be preferably the best if it's placed as an equatorial connection bond for the chair conformation to be more stable. And regarding this, this case, we definitely know that NH2 in an equatorial position will be so much more stable and better than an axial position. So the first one will be the best one or the more stable one. Because of the position of our amine group in the equatorial placement rather than the axial one. For the second one, at first we need to name all the carbons in the ring. If you start from here, like 1, 2, 3, 4, 5, and finally 6. Then we have this chair conformation. 2, 3, 4, 5, and 6. For carbons number 1 and 2, there are some extra branches other than H bonds. For example, for number 1, we see the connection bond as a dash bond. So it's placed under the surface of the ring and even under the carbon number 1. And the place is right here at an axial position under the carbon number 1 with the 2 methyl groups. And for the other bond, there's only one H bond for carbon 1. And for carbon number 2, as you can see, the dash connection bond is at the lower level respect to the surface of the ring, so it's gonna be placed as the equatorial bond to be placed under the surface in the chair conformation. So we have one methyl group right here. For more clarity, I write down the other 2 methyls for carbon 1. And the other ones are just CH connections and bonds at either equatorial or axial positions of the other carbons. Okay, this is the first conformation, the chair conformation that we created for this compound, and the second chair conformation will be a different one with a different twisting angle. It's going to be something like this, and we start our ordering from this side: carbon 1, 2, 3, 4, 5, and 6. And the connections of carbons 1 and 2 are our main concern, because for carbon 2 we need to have one dash connection that's going to be placed as the axial bond for carbon 2 connected to one methyl, other to one H. And for number 1, as you saw before, the dash connection bond is going to be placed at the surface, is going to be placed under the surface of the rest of the carbons. So the only possibility for that is being placed as an equatorial branch. So we have the 2 methyl groups, somewhere like here, and the top one is the H bond. And for the other carbons, there are only H bonds, I mean CH bonds. Okay, in terms of the difference between the 2 chair conformations, At the first conformation, we have the bulkier branch, that is the two methyl groups right here, as an axial connection to the twisted chain of carbons or the chair conformation, and the less bulkier one is placed as the equatorial one. But for the second chair conformation, we have the connection bonds in the opposite way. So the less bulkier one for carbon number 2 is placed as an axial, and the bulkier one is placed under the surface of the chain as the equatorial connection bond connected to carbon number 1. So as we prefer to have our bulkier branches in the equatorial connections and bonds, we choose the one with the bulkier branch in the equatorial position. So the best state, or the more stable state among the two choices that we have right now, is number 2, because we have the two methyl groups in the equatorial position rather than the axial position right here. So the right one is more stable. And our answer. And as you know, for part A, the left was the more stable, because the amine group was placed in the equatorial position. Okay. Thank you for your time and patience.